All right, hello everyone. Welcome to VSPG. Today we're hearing from Professor Derek Wyman. He's going to be presenting on an episodic progression towards plate tectonics. I'll go ahead and get Professor Wyman introduced. So Professor Derek Wyman is an associate professor of the School of Geosciences at the University of Sydney in Australia. He completed a PhD at the University of Saskatchewan on Archean socionetic lamprophyres of the Superior Province and their significance for tectonic and gold hydrothermal systems. In the mid-90s, he was a research associate at the University of Saskatchewan, supervising a project that analyzed 2,500 mainly Archean volcanic samples in an industry-supported study of volcanic rock geochemistry versus massive sulfide distribution. He then moved to Western Australia as a research fellow and continued work on Archean geodynamics and ore deposits of the Yilgarn craton. In 2000, he took up a continuing position at the University of Sydney, where he remains. He has collaborated extensively in petrological and geodynamic studies with the Guangzhou Institute of Geochemistry, Chinese Academy of Sciences, and other organizations in China. Working with Sydney's EarthBite group, he supervised research on the tectonic and metallogenic sequences of Phanerozoic mantle plume and large igneous province interactions with plate boundaries around the Pacific. Thank you, Derek. We're excited to hear from you today, so please take it away.
Thank you very much. It's a pleasure to be here and give my version of this story about the movement toward a plate tectonic system. So the reason I think it's episodic is or it was episodic, is, for example, compilations such as this, the zircon, uranium, lead, hafnium isotopes, as compiled here in Griffin et al. It appears to show certain events at particular times before, clustered before 3.5 GA. After that, there does seem to be a real pattern, particularly with volcanism in greenstone belts, that's global. There's big times for these events. That suggests we've got a global process going on. Can't be sure, but I would imagine that by 3.5, um, uh, these were mantle processes. The earlier ones, I have no clue as to whether or not it was driven by mantle processes or bolide impacts or whatever. So where do we start, or where do I start? I begin with my orogenic lamprophyres at the end of one of these cycles. So back in the 1940s, 50s, and 60s, the old timers used to believe there was an association between these lamprophyres and gold deposits. What I was looking at was trying to clarify the Archean tectonics of the time. If you can believe it, we couldn't all agree on what the tectonic processes were. So we had to look at the tectonics and the gold, which was often considered to be a separate Archean style of gold, and find out where the lamprophyres fit in there. And basically, it did seem to be a continuing pattern. Okay, so the thing that's interesting about these lamprophyres is their combination of compatible and trace element and incompatible trace elements. They've got high light rare earths and pretty high nickel and chrome, those sorts of things, while also being water and carbonate rich. They tend to be late in the orogenic cycle. They're associated with sanucatoids and cyanites, where these things are present. So they in the Abitibi, where I was looking at them there, the first thing that I could say in retrospect is that they seem impervious to the challenge or the alternative model that emphasizes a plume plus crust origin for most Archean igneous rocks. The compatible and incompatible elements don't really work that way, high MgO contents, etc. Plus, they've got zirconium hafnium troughs, and the oxygen isotopes told us there was likely sediments in the source. This is a feature that in the southern Abitibi became more prominent in a few rock types towards the late end of the evolution there. So all of those things uh, back in the early 90s or late 80s convinced me that we were looking at a story which is very similar to the modern one. These patterns could be from lamprophyres that 100 million years old. So it all looked reasonable to assess it in terms of a plate tectonic model. Here's just a more recent paper from the Yilgarn, where the lamprophyres are through the middle of the craton here. But the granites here have a range of isotopic features, epsilon ND from -1 to 5, whereas the lamprophyres, all these green squares here, cluster around Chur. And so, as this paper says, it seems plausible then that the enrichment in these lamprophyres is not happening right underneath their the places where they rise to the surface. It's happening at a subduction zone on the eastern margin of the craton in the late Archean. So this doesn't support a vertical origin from link to drip tectonics, for example. So the association with gold then was not seen as a direct one. It's not a perfect match. Sometimes you find the gold without the lamprophyres. Sometimes you find the lamprophyres without the gold, and so it's having gone through a period where people have said, of course, that the gold came from the lamprophyres, and that is now widely recognized to not be the truth. It brings us to the idea we had two independent expressions of the orogenic process here. So we're not just looking at one rock type to infer tectonic context. We've got the rock type, we have the gold source, okay? Now, you can't just throw a bit of water down there and say, okay, and there's the water we're going to get for our gold. It has to be broadly similar to the fluids that have been associated with gold right back to the late Archean here. Okay, so there's that context too. You can't just have any old fluid. You've got to have this kind of a fluid there in terms of what's being mobilized, what's not being mobilized, the pH, the pressure, temperature, and those sorts of things. Okay, so as a collection of observations or events added to orogeny, it's it's something that you can compare to more recent times, and the more you add to it, if it stays the same as more recent events, the more difficult it is, I think, to suggest a viable non-plate tectonic alternative for these things. Okay, so by about 1990, we're pretty much done with this. The lamprophyres, we thought, I still think, demonstrated a sort of a plate tectonic style of origin. And we thought that was all that the lamprophyres could tell us. There was still, at that time, plenty to learn about the actual orogenic gold systems, but that seemed to be it as far as this particular story had gone. But then, in 1996, a prospector found bedrock diamond in the Wawa subprovince. And within a few years, this worked its way through the system, and the Ontario survey asked me if I wanted to look at my old rocks because they've now got diamonds in them, which was kind of a shock. So I said yes, I wanted to get to be a part of that. Turns out the diamonds are quite variable with cratonic and eclogitic inclusions in them, color and form. They're all rather complicated. Not being a diamond expert, that just added to the complexity for me. We studied xenoliths from these things. There's a wide range of xenoliths. This is one particular type here. There's multiple types. And it was determined by bulk sampling and just eyeballing that diamond abundance correlated with the abundance of xenoliths, but nobody, as far as I know, ever figured out or proved which ones the diamonds were in. Okay, so this is indicates a subarc mantle with the classic features of a subduction zone kind of setting, formed at the base of the crust. It wasn't an inherited pattern found later. Well, the thing about that finding is that you're not supposed to get diamonds in Shoshonic lamprophyres because they originate too high up in the mantle, and that was the main challenge straight off. But that challenge had been faced by previous workers in Australia, where Southeast Australia has 500,000 carats of placer diamonds and no cratonic root. And the models vary slightly between these two sets of authors, but they all involve a subduction process. So what Griffin et al. Said was that they envisioned the possibility of a lamproite coming from the diamond stability field, smashing its way through the slab or somehow a tear or something like that, to get the lamproite product up here into the shallow crust where it deposited the diamonds. So that's where it stood because they didn't know the host rock type. And as far as they knew, presumably this was all a one-off, so they didn't have to make it something that would happen all the time. But as I considered this challenge, I found that this was actually not a one-off. So here's a better figure of the eastern Australia. This is the Bingara-Copton area, after which the diamonds are named, so they're most abundant there. Here's the Hillgrove's gold deposit here with lamprophyres in it. So we've got gold diamond lamprophyre association there. And then I found out that in the Motherlode and district and others in California, they had historically found diamonds in the old workings when it was done by hand. Not sure about the accounts of the lamprophyres there. There are reports that mention them, but I don't have any good quality data on them. So we're getting an unusual occurrence again, where there's no craton under California to suggest a normal host for these things. Then in Desheen in Guyana Shield, there were rocks that had been called Comadiites by Captain Violet et al. I looked at the data and I found them to be very close to the Wawa breccias. Okay, so I when I first published on these things, I said, well, they look the same, and I think they are the same. And then I found out retrospectively that McGee and Taylor in an ANU annual report had actually had some of these rocks, and they called them Shoshonites. Okay, so I was very happy to hear that. Then we go over to Ghana, and we have the Barim diamond field here in the blue, and the Ashanti gold fields. People over here had found the host rock, but it was a highly weathered kind of diatremes, and whoever the authors were, considered them to be very similar to the sheen. So loose chain there, but you could reasonably say, well, then it's likely that they are similar, same age and everything. So it's quite likely then that we are seeing rocks similar to the Wawa rocks there. And then you go back to the oldest Shoshonic lamprophyre I know, is at 3.12 in South Africa in the cup wall, and I found out that reading through the diamond literature, there were in fact diamonds in the Witwatersrand. They only found them back in the old days when they were more gentle in their extraction of the gold. So here we have then a repeating series of events and an association going back to the precursor, the source region of the Witwatersrand gold. Okay, so knowing all of that, I need to come up with an idea that could be reproduced, plausibly could happen over and over again. So my suggestion was then to warp the subduction zone into a more of a flat kind of a setting here. When you do that, you warp the thermal patterns, of course. You freeze out any mantle wedge that's there, and you get the diamond stability field actually occurring along the boundary between the oceanic crust and the overlying mantle. And so, depending in the real world, this would probably be metastable. It might happen off and on again as you go down this part of the subduction process. Once you dip into the mantle, you get the more conventional diamond stability fields. So this setting, you might recognize it from Gutsche et al., but others have said the same things, is widely known for having streaks of slab melts going through it. You get Adakitic type things. Slab dehydration is focused at the bend, but it goes down here. So over time, this bend would have moved down and would have sort of focused fluids all the way down until it gets to here. You've got your diamond areas, and you've got what is essentially, if this is all right, a synucleoid nursery, which is great because the synucleoids occur late in the evolution of a greenstone belt, and depending on where you want to put the line, Shoshonic lamprophyres can be considered a part of that group. Okay, so that was my best shot at trying to explain these things, and that's where I've left that idea. So I believe that in the Archean, we were able to get orogenic events that resembled the modern ones, where the oceanic crust was shallowly subducted, but not so shallow that there was never an asthenospheric wedge there to start with. Okay, now if you try to provide an alternative for this, the most common one would be a drip process. Depending on who you read, the drip has got numerous possible melting zones in there, some of which might apply to lamprophyres. Others, like this melting in the asthenosphere, are said to be dry, which of course doesn't match the lamprophyres at all. I just note here the survey of 27 proposed drips post-Archean had at least 26 of them were in tectonically active continental regions, so they're actually being driven by a plate tectonic process. So when I compare these two areas, these two concepts, then I don't like the drip for a number of reasons. It's a single pass; it only brings you one load of water. Its impact on the mantle in terms of temperature are quite low. There's no trap in the mantle to concentrate the volatiles. The models assume that the drips are H2O saturated, but it's never proven. And that's why I've got this feature here. I'm not even sure whether or not the drips lose their water right at the start back up into the crust. The distribution of drips is sort of chaotic in the sense that I don't feel it's as reproducible as the orogenic subduction model. Okay, and then there's the fact that these drips are used to explain a wide range of rocks from bonanites to siliciatoids, but they have to show up at the right time in the right place. Okay, so you got those are constraints that are actually hard to do. And it's never clear to me that drip models can actually do that, give you them at the right time and place. The subduction zone, of course, has got all the things that I think are important here. Sustained water being added to the mantle, modification of the mantle thermal profile as needed for the diamonds, a mantle wedge to actually trap these volatiles coming off of the slab, an ability to take sediments down into the mantle, and a distribution that is consistent with all of the things that I have talked about. So have to leave that there. I'm just saying that I think that since at least 3.1, we have been able, well, Earth has been able to replicate the key features of many of these origins. So I think that we've established a hydrous metasomatism of the wedge in the late stages, which suggests to me it was feasible early on. I note that these greenstone belts have usually got multiple rock types in them, and that in any given belt, they usually vary from flat mantle normalized patterns to more enriched later on, which is not really the same as, say, the Proterozoic North American mid-continental rift, where they start out enriched because of they're contaminated by their crust, and then they transition into flat patterns or flatter patterns when the magmas are more associated with the mantle rather than the crust. Okay, so there's no way to go through many greenstone belts here, and I'll just highlight a comparative recent study by Jack Lowry, my former PhD student in the Western Yilgarn. There, we've found greenstone sequences from 2820 in a stage one, and then shortly after that, a second stage. So these start with picrites and lots of cumulate rocks. They move on to mafic, ultramafic rocks. As you go through, you see a variety of rock types of fairly short order, okay? By the time you get to 2799, you've got first manifestations of some rocks showing zirconium hafnium troughs there, various incompatible ratios versus the high field strength elements there. And then by the time you get to around here, you're starting to get lots of hornblende in these rocks. So there's quite a bit of water in them. And then by about 2790, let's say, you've got bonanites and bonanite-like rocks showing up in the sequence again, along with various other mafic rock types. And then the stage one goes on towards SHMBs here, and granites of various type, including those with hornblende in them. So briefly then, why would you get bonanites here? It can only suggest that after an initial event at the start, there was a re-melting of those same rocks in a relatively short time later, of that same source rather. So in stage two at 2750 roughly, we get again shoshonic lamprophyres and trachy andesites in it. Okay, so a wide range of rocks that you need to account for, and that makes it somewhat challenging. If you got isotopes in there, it explains a few things. Many of the rocks appear to evolve along a line related to fluid metasomatism of the source. There's other rocks that appear to have been either modified by crust and or sediment in the source, or as they're rising up through the crust. I would say there's probably going to be some of each, given that the lamprophyres, for example, are likely had sediments in their sources. So here we see the fluid metasomatized rocks, several patterns here of how magmas are departing from uh, you know, near zero epsilon and d, and indicating that a couple of processes are going on there. So all of that complexity, I think, is best explained by a subduction type process. Here's some key observations from the eastern Yilgarn. Um, there's an area called that Jack was studying called the Q isotopic zone here. It's an area that is now thought to have been an attenuation of 3050 to 2920 crust for this event, this stage one at 2820. So there seems to be almost no deep crust there. So the region has got a few 2900 zircons in it. All of the really old zircons are outside of there, but and then you've got the igneous and xenocrystic zircons from the magmatism. So the most popular idea at the moment is that this zone represents a feature linked to a subduction process, let's say where the Naria is, okay? And so if that's a suture there, then this becomes potentially a back arc rift. All of those rocks you saw on the last slides, and the ones I didn't show, involve no plume rocks. There's no cobatyites or cobatyitic basalts. So we've got this craton evolution here that is plumeless at around 2800. So standing back again then and looking at the work of numerous authors, we have what are claimed to be subduction related or arc related rocks all the way around the Yilgarn craton in this 2800 to 2700 window here. And we've got some also right in the middle here. We've got the lamprophyres going through there. Okay, so that's what it looks like by the Neo-Archean if you don't think about the mantle plume being in there. So have to stop talking about that, unfortunately, and move on to a different but linked subject. There's issues with the use of ratio plots here. Julian Pearce, you all know these things. Julian Pearce came up with these. You've got trends here which are parallel to the mantle array, and if they are nice and parallel to it, then it's considered to be an arc volcanism related to hydrous metasomatism. So that gives you one distinct path. If you get a contamination of those magmas, you get this kind of a trend where it moves up into the still moves up into the arc region, but it follows a more evolving process here. Now, so many workers find this kind of a result in their Archean rocks, and they immediately say it's a contamination trend. I've said many times and been ignored many times that it's not necessarily that, okay? The contamination could, in fact, be slab melts in the mantle. So Julian did actually slightly address this in several of the papers, but it was never his main issue, right? So in the original PS 2006 paper, he said that proponents of a subduction origin to hotter attribute these features to hotter subduction with more common slab melting. Okay, that would be Kerich and myself and others, right? But so Julian is mainly notes, however, that the data was still plot above the Morb array, okay, consistent with the selective enrichment of thorium. Okay, so he's not saying it doesn't happen. He's just saying that when it does happen, this is the effect you get on the plot. And then in the more recent Brown et al. Paper, It says experimental melting of the Norwegian ridge, like basalts under the conditions that RAP is using, still generates melts that will react with the mantle wedge to produce primitive arc magmas that plot in the VAB array. So he's not saying it doesn't happen. He's acknowledging that it can happen and that it will be in those regions where the contamination process would happen. But this has not been appreciated enough, I don't think. And we find this getting into papers such as this one here by Smithies et al. They found the two trends to be present in the Archean, the parallel trend and this evolving trend here, all right? And and they attribute this variable THNB trend to interaction of mantle-derived magmas with the crust, and that they were not linked to a subduction process. Now, the rocks he's showing us not linked to subduction are most famously attributed to subduction in the Archean, right? This is the Abitibi Greenstone belt leading to the Blake River and etc. Right? So that's often called a subduction process, and so he's got a different view about what that plot means. I point out his Smithies et al. 2005 modern subduction processes in the 3.12 Wundo intraoceanic arc. Here they identify hydrous fluxing and also an increasing slab melt component in these rocks as you go up the calc-alkaline pile, culminating in the eruption of Adakitic rocks. So they've plotted those rocks there, and that bolded statement there is exactly what I would have said about the Blake or the Southern Abitibi and the Blake River group and etc. So as you go on, as they evolve through time, you get closer and closer to Adakites, not further from them. Then at the end, you actually get Adakite magmas coming out, all right? So for decades, it has been suggested that slab melts and the typical background upper mantle melted in things like the Blake River group to give you the array of compositions that you find there. Okay, right. So I have to move on from that to the issue of proto-arcs and mantle plumes. These both have got high Mg rocks in them, but sometimes they can occur in the same greenstone belt quite closely. But there's a number of points you have to keep in mind that I'd like to emphasize here. I've done this previously. Going back to the Margi area in Troodos, we find there that they had ultramafic flows, dense in olivine, and they were initially thought to be primary magmas. Later on, it was understood that they resulted from olivine crystal settling in high-level magma chambers or within flows. When you get these magma chambers relatively close to the surface, you dump all the olivine in the bottom, and then you extend the crust. You can apparently, push these things out to make individual flows. And we found that in the western Yilgarn, his tubes that are in a 2.8 billion year old sequence, and it's just full of these olivines, and so it's an example of this remobilization. The lava tubes had MgO to 36 weight percent, but we never found any true co-magnetic rocks in the area. Okay. So just in case people think I'm stretching the limits of credulity here, I'd like to point out these North Georgia rocks. Okay, so these are young rocks in an understood setting here. This is the figure comes from Pierce and Reagan's supplemental file. I've added the primary composition of the magmas from this earlier paper here. So you can see if somebody returned this data from an Archean Greenstone belt, they would likely want to say it was a comadiite sequence, but we know that it wasn't in this case. And I'm saying this happens quite often, that you get this kind of procedure going on from the pickrite field, right? So you don't necessarily have to be basalts doing it, but from the pickrite field, you get this evolution here. But it's something that we need to keep in mind all the time. When it comes to spin effects, the pyroxene spin effects is tricky to reproduce in the lab or in a systematic way. And the observations from the field are very important. You will find people describing rocks as chromatic andesites and this sorts of thing, relatively low MgO, but they've got pyroxene spin effects in them. And as observed in this paper, the range of compositions indicates that pyroxene spin effects is actually controlled by the thermal characteristics and the depositional environment of the flows, rather than just the composition of them. Okay, and it was suggested in this paper that it was facilitated by emplacement into shallow water, which I think happens fairly often in the Archean. So I beat this topic to death in several of my papers. Jack describes more of it in his papers there. Don't really have time to go into it any more than that. It's important if we're going to get an accurate grip on the proportion of plume rocks in these cratons. Redmond and Keyes said many years ago, 1985, that silicious high magnesium basalts were in fact a real rock type, not just a contaminated plume rock. They got a lot of pushback on that. I think that they were right, and SHMBs now show up in the Pierce and Reagan plots. So I think that they are real, and it's not that hard to get these pyroxene textures. Okay, another thing you'll hear, and I've said this in the past too, is Archean greenstone sequences typically begin with comadiites. I've said that in the past, just quoting others, but when you actually look at it, you realize that could be a misleading comment. Okay, so we've got these 2720 and younger comadiites here in the Yilgarn. And if you just work in that area on those rocks, you'll see these things coming through older crust. And if you've got your head down and that's what you want to study, you might forget about all these other people looking at these other rocks all around that are indicating there was subduction processes. Okay, so this, look, first of all, that shows that the comadiites post-date the subduction style magmatism in this cycle. And it emphasizes this point where it's too big to fit in there, okay? So that becomes a problem. It's too big to fit in there if it's a core mantle boundary plume. Right. In the Abitibi belt, this well-known stratigraphic column for the southern Abitibi shows the known units. Later on, they added this calc-alkaline unit down here from 2766. And so we've known about this part the whole time. And the comadiites, so-called, that's meant to have started this sequence, they're right up here at the top. So you've had other magmatism going on for a long time prior to that. If you read the descriptions of this unit here, you see that they are abundant tholiites and lesser comadiites and calc-alkaline volcanic rocks in the upper part. All right, that was 2002. If you think about that, lesser comadiites and calc-alkaline rocks in the upper part, it seems a bit strange. You know what I mean? and especially since the overlying rocks have got no comadites in them and are entirely alkaline. All right, and then Sproul in the same year noted that there was much less than 1% by volume of komatiitic rocks in the Paco. Okay, these rocks are komatiitic basalts, low Mg komatiites, and cumulates. Okay, well, in the perspective I've got now, I find that all kind of fishy and suspect. Okay, so I plotted them up on the Pearson-Reagan plot, and I found here that two of them plot in the komatiite field here, but only one of them here, and many of them plot in the boronite field, and many of those plot the same way here. And I have to note that Pearson-Reagan said, this line is not well defined at high NGO to distinguish between these two rock types. Okay, so put that out there straight away. But it doesn't uh, it doesn't show me that they are komatitic rocks. I think it makes much more sense if it's actually a proto-arc developing for the overlying sequence. So I believe that is not mantle plume, and it's the beginning of this sequence here. Even if you don't believe me, you've still got to recognize that the thing didn't start with a plume sequence here. You've got all of these rocks earlier. So it's a commonly made comment, but it's not accurate. And this is important because what we need to figure out is we all know that there's an association of plume and arc style rocks in the Greenstone belts. We have to know for sure if there is a pattern and which one comes first. And I'm saying there is a pattern and the arc rocks come first. Once you've said that, it changes the spectrum of possible models that you might apply there. So we found out there's quite a number of these rocks, sometimes having been called komatiites because of a bit of pyroxene spin effects and boronite. So there's a number of them. The Opatica that Boyle and Dion reported on, the low titanium rocks that we described at the Kidd Monroe sequence, that Paco sequence that I just showed you, I'm calling it one of these. Shabandoan, Lake of the Woods, etc. Okay, I've shown on there the red opal, which is the small thermochemical plume suggested by Dostal and Mueller. Note how different it is from the core mantle boundary plumes there. Okay, so why might that happen? Why might you get so many of these things cleaving into existing cratons, as in the Yilgarn? Well, it could be related to the significance of the Mantle Transition Zone at that time. If the transition zone was a more powerful feature, as I will argue later, then it's going to make marginal bases very close to the trenches. It'll keep clipping off the margins of cratons in this kind of environment here, as we saw in the Yilgarn. So Hill and co-workers made a good case that Phanerozoic plumes come from the core mantle boundary. Uh, and then they applied that to the Yilgarn. And I think that's where they went wrong. They estimated that in the Yilgarn, these plume heads would be 700K wide before they got flattened in the upper mantle. They thought it might give you an equal area of 2000K wide magmatism. And they noted ages of, say, 2715 for the ultramafic magmatism and then younger felsic magmatism later. Well, that's not technically not correct, but it's just the wrong perspective. You're talking about mantle plumes that are like 2000K wide, right? And you've got to consider all the other things that were going on at that time. So it's not consistent with what we now know. While I'm hacking away at mantle plumes, I return to the Pilbara. One of the ideas that's been applied to the Pilbara is this many plumes idea, and it's just inconsistent with what we see there. We don't get enough granite blooms after each one of these. And in fact, the 3.4 GA rocks are pyroxene spin effect komatiitic basalts in terms of the authors, okay? No actual komatiites until 3.27 at Ruth Well. So I would look more closely at those rocks in the Pilbara then, okay? While we talk about the Pilbara here, the idea of convective overturn seems to be increasingly challenged here. I think we've had some talks in this series, and there's other evidence that it doesn't persist greater than 10K in the surviving crust out there, okay? So a lot of the standard models for the Pilbara are again in a period of flux, I think it's fair to say. Well, one of the issues I found with the Pilbara was that the Wundo bonanites at 3.1 GA were described as the first Pilbara bonanites and were widely cited as the first real bonanites out there. But as I plotted up other data, published data, I found that the 3.25 sulfur springs and 3.3 GA Euro basalts also included rocks that fit within the Bonanite series, as well as the Wundo group did. Okay, now these have previously been called depleted basalts, but according to the Pearson-Reagan plots, they are Bonanites, and that to me is an important observation. So the amount of depletion in these Pilbara examples, which are the square symbols here, are very similar to one series of depleted bonanites in Troodos. Okay, so we do see these things over a long period of time, dating back to 3.3 GA, and they're quite similar in terms of their features, their trace element patterns, and those sorts of things. Now, here's an interesting issue about the Pilbara. Some of the oldest volcanic rocks, there are some slightly older intrusive rocks. The oldest volcanic rocks, apparently, are these 3.5 GA rocks here, the Kukul formation. There's slightly different versions of it, okay? And they are associated with TTG flows of about the same age, okay? Now, it's been said that these are a suitable source for the Pilbara TTG, and that their enrichments can't be from TTG because there weren't any TTGs yet, okay? So these were cited as potential precursors then for the Pilbara TTG. But without a subduction process, it becomes unclear as to how these things were developed in the first place. So Smithies et al. So the geological processes led to these sources were restricted to the earliest period of evolution in the Pilbara craton. I looked at those rocks and I thought, that looks like the Blake River group, okay? Now, watch your minds here. This is the Betamax of ratio plots from fitting it's backwards to the conventional Pierce ones, okay? So niobium yttrium over zirconium yttrium here. I've plotted the Kukul formation basaltic andesites here on our old plots of the east and central Blake River group. You see that they fall right along that trend there. The Kukul Adakite is there. The Abitibi Crist formation is there. Round Lake batholith. Sanucatoids from about 3 GA here, okay? So this is an indication that those Kukul formation rocks are not that unique. In fact, they aren't. And I infer that they all reflect the input from Adakitic melts, okay? So this goes back all the way. There's no particular mystery about that. Those rocks showing up there. Okay, so we have to know plumes or arcs first. And since everyone was saying it's plumes first, all the modelers went and tried to develop explanations for it. And there's a lot of those stories out there. But now we know the plumes did not arrive first. The spatial restrictions on a map suggest they were quite small, and we learn that they are damp. Okay, so in this paper, um, they found zero point 0.6 weight percent H2O in these things. Now, this had been said earlier. Shimizu et al. Had claimed 0.8% weight percent in their comadiites, inferring that they came from the transition zone, but that was largely ignored. It was claimed that it was an alteration process, and so that just got just set by the wayside. Jeffrey Davies again came up with a model for plumes based on a feature he calculated existed at the transition zone, mantle transition zone boundary, a basalt barrier. Okay. Now, this didn't get all that far either because by this time, 2008, everyone was so onto the core mantle boundary plume like this that this couldn't fit. Okay. But it turns out that if the comadiates are in fact damp, this is a needs further consideration. Now, I'm not going to claim that this 2008 paper has it perfect, but I think it's really on the right track, and that Shimizu was right, and as has been shown by other workers since then. So when I go back to look at the Yilgarn, then I see a small mantle transition zone plume here, ringed by subduction processes. And that would be consistent with the size, say, of the inferred plume in the Abitibi belt. And the variation in the compositions here is because it's actually a thermochemical plume, not merely a thermal plume, right? So the variations can, to at least some degree, be attributed to variations in the composition of the plume. It's like it's got streaks in it, for example. So if we go back and look at where the plumes arrive, we find that in the Superior Province, near the end, it was associated with convergent margins. It was after arc volcanism had started. Subduction zones have been inferred to operate in both directions, at least locally. Okay. And then if we go to an example from the Circumsuperior Province, where we've got these comadiatic type rocks here, it turns out that they formed late in the development of the Circumsuperior belt formed late in the subduction evolution here, when most of the outward facing subduction zones flipped inwards. After they flip inwards, we get the circum-superior rocks coming through here. Okay. If we come up to the youngest example here, the models for this region have included, like Waterman Stern, for example, a plume first model to account for the association of subduction rocks and plume rocks. That depended somewhat on the position of the Galapagos plume, which was not in the right place. And it was assuming that people were telling the truth when they said that in the Archean, the plumes come first. Well, for both of those reasons, that one is cancelled out. If we look at the plate reconstructions of Pindel et al., however, we see there's a flipping of subduction zones here that happens by itself. It flips this way at first, and it's been going this way for a while, then it flips the other way. So you've actually got hanging slabs for a while there, right? You've got the old one dipping east, then it flips and dips west, and eventually you wind up with this situation here. and you've got the Caribbean lip in there, surrounded by subduction here. You've got your only example of young comaditic rocks, and these have also had a subduction influence in their trace element compositions, according to those that worked on them. So, based on all of that, then had to come up with a model that would work that was craton centric, so to speak. And so, whereas many hypothetical associations here had shown a plume ringed by subduction zones, I have a craton ringed by subduction zones, or at least, let me correct that, subducting slabs. I don't want to get to plate tectonics. Okay, so you've got these localized subduction zones here, and they generate or help to generate this mantle plume by this kind of a process here. So there's many ways you could move, get this kind of a process. Patrice Ray, for example, talked about a kickstart, right? And so you could either kickstart it by flattening the craton, or more globally, perhaps, you could have it happening in response to changing intensities in convection of the mantle. And since we get these at different ages, we get different cratons, but similar ages, I prefer some kind of a link to the convection process in the mantle. So as I see it, then you've got background stagnant lid, you've got this upsurge in convention, driving the craton one way or the other. The surrounding stagnant lid wants to subduct if you give it a little bit of a push. So you push it, you get a localized start to a subduction style process here. You get the generation of some new crust here, mainly by asymmetric spreading. You're not in a world of linked plates. You get asymmetric spreading, replacing the subducted slab. But the actual subduction doesn't last very long at one point, but it continues around. So it runs, it radiates out from that initial point, because all of the old slab is also wants to subduct as well. So I see this as kind of a peeling away of old slab in a focused manner. It drops the stuff into the mantle transition zone, and often generates a komatiite-bearing plume as a result of that. So what the effect of this is to give the impression of Volbara supercontinents, but in actual fact, they are two different cratons that evolved in response. Well, they existed, but the history was related to the mantle processes. So that's what I'm offering up as an idea here. Okay. So in summary, episodic crustal growth is likely driven by cyclical mantle processes. Cratons probably facilitated and focused subduction type events. Growth of cratons might have happened by back arc rifting. You just like chip away and grow it. That would have been a very common process. Plumes repeatedly occur after arc style rocks, so they cannot be coming from the core mantle boundary. Damp plumes originate in the transition zone or near it, where focused slab breakthrough is eventually compensated for by upwelling of the lower mantle, which takes some dampness with it. When did true plate tectonics start? I don't think it started until the Paleo Proterozoic. And that was related to bigger cratons, longer plate boundaries, and the demise of the special features in the transition zone, if Davy's calculations are correct. Sorry, I went rather long, but that's it.
No worries. Thanks a bunch, Derek.
Thank you.
We'll transition to question discussion. Derek is happy to answer questions for a while here, so you can ask questions by finding that react button at the bottom of your screen. Click the raise hand button when that pops up. Or you can type your question in the chat and I'll read it aloud for you. First up, Paul Hoffman, please go ahead.
Yeah, I think that moist, shallow plumes from the mantle transition zones are a very fertile area for investigation, and I think is also quite compatible with plate tectonic
Yeah.
regime. And I am reminded that Norm Sleep back in the last century pointed out that in the Archean, deep mantle plumes should be much less significant because there was a smaller temperature drop across the core mantle boundary due
Right.
to more intense radiogenic heating in the mantle.
Right. Right. Well, that's a different take from the Davies approach, but it's both worthy of consideration. Yeah.
All right.
Talk
Let's
to
see.
everyone's ear off today.
Don Anderson would be pleased.
Right.
And we'll give people some time, a little bit here if they want to, if
So
we have
there,
more questions brewing.
in your model for formation of diamonds, it doesn't
Yeah.
require thick lithospheric kills, or you think it was a sort of growth through flat subduction? Can you expand a little bit on it?
Are you asking how the sediments get into the mantle?
No,
Sorry,
how diamonds
oh, the diamonds.
formed in your
No,
model?
they in this model they are shallow mantle diamonds. It's that you perturb the geotherm, and that brings you the diamond stability field up to a shallow area, and it allows you for them to be sampled at the depths that the Shoshonites would be at. It also can account for the variability of these diamonds. They're a total mess of sources and links, which are just bouncing around between the overlying mantle and the slab. You're making diamonds in both of them. You might be rolling around the sediments on the top of them and that sort of a thing. So it's a very complicated kind of environment. So it's the temperature change, and by this process, of course, is a powerful one in terms of modifying the temperature locally, and so it gives you perhaps the ability to minimize the hot Archean processes. If you can get this thing going, you actually cool down a certain sector of the upper mantle and crust where the shallow process is going on, at least for a while, right? So it sort of changes what you might expect about the thermal profile because of the intrusion at shallow levels. A very abrupt change in the from the standard gradient, right? So that's something to keep in mind also. Yeah.
So this thermal perturbation or thermal change is due to flat subduction?
Yeah. Yeah.
Okay, thank you.
Yeah.
Yeah, the issue with the diamonds is with the stable isotopes, the carbon and oxygen isotopes, which indicate organic carbon source for the carbon, and the oxygen isotopes and the inclusions in the diamonds indicate equilibration at low temperature.
Right. Yeah.
So
I didn't actually analyze the diamonds, but other people have. Yes. Yeah. Yeah.
Okay, if there are any other questions, feel free to speak up.
And next week we stay on Archean, but we switch to Archean life, and Sugitini will talk about oldest examples of Archean life from Western Australia.
And it will be a Pacific afternoon time presentation next week. We haven't nailed down the exact time, but working on it. Thanks so much, Derek. This was a really great presentation.
Thank
Fun
you.
time. Thank you. Thank you very much. Bye-bye.
All right. Bye, everyone. See you next week.